Okay, so now let's see for our result. For our result, it's application. It's application. So it's the application. Still the result in section 5.3. 5.3. But it's the application. So it's an application. So first of all, we give some data. So it's a pair. It's a pair A and B, A, B. So the data is this one. So we have A1, B1, or A2, B2. We have several points. A3, B3. Later I will give you the example and so on. So the general result is this one. We have this one. Okay, we have several data. For the data, we have this one. Yeah, it's the data. It's the data. And we want to find our question is there. Our question is there. It's our question. We want to find a linear function. A linear function. Y equals C1 plus C2x. That best fits the data. That best fits the data. Best fits the data. Yeah. Okay. So what does it mean? What does it mean? It means that here we could build it this way. Here we have an XY plane. Here is our XY plane. And we have several data. For example, here is our A1 and our B1 is over here. So we have a point A1, B1, and A2 is over here. B2 is over here. So it's probably here, and A3 is here, and we have B4, B3 is here. So it's probably here. A4 is here. A5 is B5 is over here. Probably is over here. B5. B5. For example, this one. I erase E. For example, this one. Okay. And then now we want to find a linear function. Y equals C1 plus C2x. That best fits the data. It means that we want to find a linear function. Linear function C plus a constant plus x times a constant. It's a linear. It's a line, a straight line, right? So it's a straight line. So it means that we want to find a straight line, right? And here, once you plug in the value A1, then you will get C1. For this, if the function y is what we want, if the function y is what we want, it's what we want, y equals C1 plus C2x. Then once you plug in the value, the x value by A1, you will get here is our C1 plus C2A1, right? And here plug in the value A2, you will get is our C1 plus C2A2. And here is the C1 plus C2A3, C1 plus C2A3. For the value, oh sorry, it's not here. It should be A3, it should be here. It should be here. And the A4 is here. Yeah. So it means that we want to find, consider that here we have for example, here I just use 4 data. So in the 4 data we have the vector. Let me see. Here we have. We consider the distance. We consider the distance. Consider the distance. Consider the distance. Consider the distance. Yeah. And for the distance, probably some of them is positive, some of them is negative. I mean, this guy subtract this guy, then it's negative. This guy subtract this guy, and then it becomes positive. This one subtract this one is negative. This one subtract is negative. It's positive. So for their length, we consider their square and consider their sum. Sum of square of their length. Sum of square of their length. And to minimize. Yeah. So let's call the base fits the data. Yeah. Okay. So for this argument, for this one, we could write in this way. We could explain it by this way. We consider a matrix A here. Sorry. I think I could. If I label it by this one, as we say, for this point, I write down. We have here. The first one is C1 plus C2A1, C1 plus C2A2, C1 plus C2A3, C1 plus C2A4. You see that? C1 plus C2A4. Yeah, sorry. C1 plus C2A1, C1 plus C2A2, C1 plus C2A3, C1 plus C2A4. Yeah. If we have 4 data, and for the original value, when x equals a1, a equals a1, it's b1. So original is b1, b2, b3, b4. Yeah, and we consider the length of their subtraction, and it's known. The length of their subtraction, and to minimize it, we want to figure out the constant C1, C2 such that this one is the minimum. It is the minimum. So for this question, it's our goal. So for this question, we could write in this way. Here for this vector, you could build it this way. It's the matrix. Here we put it 1, multiplied by 1, multiplied by 1, multiplied by 1, multiplied by 1. So we consider the matrix 1A1, 1A2, 1A3, 1A4. And multiplied by both of them have C1, C2. So we consider C1, C2 here. Yeah, I write it here. Here is our C1 plus C2A1, C1 plus C2A2, C1 plus C2A3, C1 plus C2A4. So we could write in this way. It's our 1, 1, 1, 1 times C1, it's our times C1, times C1, times C1, times C1. So it could be in this way. It's the vector times C1 plus the vector C2, so it's A1, A2, it's A1, A2, A3, A4 times C2. You could build it this way. Okay, you could build it this way. A3, A4. So you could combine them. It's our 1, 1, 1, 1, A1, A2, A3, A4, and it's our vector 4 by 2, 2 by 1. So it's C1, C2. It's the same. It's 4 by 2, 2 by 1. So it's still 4 by 1. And it's 4 by 1, 4 by 1. So the size is the same. Okay, so you could build this form by this way. So it means that for this question, you could define the matrix. Define by this way. It's our matrix A. It's our solution X. So here we could let A be the matrix 1, 1, 1, 1, C1, it's A1, A2. If we have four pair of data, yeah, so it's our A1, A2, A3, A4. This one. And the vector X is the C1, C2, and then the vector D is B1, B2 on here, B4. Yeah. Of course, the general case is I write down. The general case is the matrix A is defined by this 1, 1 on here, C1, C2 on here, Cn. Respect. And the respect is B is the vector B1, B2 on here, Bn. This one. Then we want to find x hat such that B subtract Ax hat, its length is minimal. In other words, we apply this square solution to Ax equals B. So that's the reason why we could use the previous result to solve it. So we have 4 pair of data or n pair of data. We have some data, and we want to find a linear function y equals c1 plus c2x that best fits the data. So our goal is to figure out the constant, the coefficient c1 and the c2, and how to figure out the coefficient c1 and the c2. Actually, you could let A be this matrix. General case is this one, and let X be c1, c2 this vector, and B is this vector. We have the matrix A. So AI is the given, and BI is given, and we want to find X hat such that the length of the subtraction is minimal. So we could apply this square solution to X equals B. Yeah, so now I give you one example. Okay, so here I erase it. Okay, so now let's find I'll give you the example. Find the best square fit by a linear function. A, B, 0, 1, 3, 4, 6, 5. In other words, we have 3 pair of data, 0, 1, 3, 4, 6, 5. This one. And we want to find the best square fit by a linear function. So if you want to solve it, just follow this one. It's our A1, A2, A3, and it's our B1, B2, B3, right? Okay, so just follow this one, we could solve it. So let A be, in this case, we let A be 1, 1, 1. We have three pairs, so here is 1, here A1 is 0, 3, 6, so it's 0, 3, 6. It's our matrix A. And the vector B is this one, 1, 4, 5. This one. So we let A be this matrix, and let vector B this one. So you could see that A transpose is 3 by 2. Because now we want to solve this linear system, but we want to find its. We could apply this square solution to this linear system. So it means that, what does it mean? It means that we should consider A transpose A x hat equals A transpose B. We should solve this equation. Okay, yeah, and so of course, once if you figure out Ax equals B, probably you could not get a solution directly. Yeah, anyway, we could check it. For example, it's our x1, x2. So it's when we consider Ax equals B, then it becomes it's our x1 plus 0 times s2. So it's s1 equals 4, 1, and the x1 plus 3s2 equals 4. S1 plus 6s2 equals 5. So it satisfies these three equations. So in these three equations, here is s2 equals 1. Here, when s1 equals 1, s2 we could get 6s2 equals 4. So it's a contradiction. Indeed. So we just could apply this square solution to this one. It means that we just could use this way to solve it, to find x hat. So A its transpose is, here is 3 by 2. So transpose becomes 2 by 3. So first column becomes first row. Second column becomes second row. Yeah. So A transpose A is the matrix. Let me see. A transpose A. So it becomes 1, the first row, first column, so it's 1 times 1 plus 1 times 1 plus 1 times 1. And the first row, second column, so it's 1 times 0 plus 1 times 3 plus 1 times 6. And the second row, first column, 0 times 1 plus 3 times 1 plus 6 times 1. And the 0 times 0 plus 3 times 3 is 9 plus 6 times 6, 36. So it's 3, 9, 45. And A transpose B is exactly 1 times 1 is 1 plus 4 plus 5. And it's 0 times 1 plus 3 times 4, 12 plus 6 times 5, so it's 30. So finally it's exactly the vector 10, 42. You could see that, right? Okay. Yeah, 10, 42. Okay. So now we could solve it. Just figure out this one. Just use this the way to solve it. So it's the application. Yeah, I mean this square solution is famous one. You could see the name in several topics. You could see the name. Yeah. So okay. So now we consider A transpose A transpose B. So it's 3, 9, 9, 45, 10, 42, and then multiply with negative 3a to the last row, you will get 3, 6, 10, 0. So it's 45 subtract 27. So it's 45. Oh, let me write down. So it's 45 subtract 27. So it's 10. 42 subtract 30. So it's 12. And it's equal to 18. Okay, and this one, and let me see. Yeah, and we divide by 6. So you could see it's 3, 9, 10, 0, divide by 6. So it's 3, 4, 3, 2. Then multiply negative 3a to the first row. So it's 0, 3, 2, 3, 0. So 10 subtract 6, so it's 4. So we should multiply 1 here, divide by 3. Finally, you could get 1, 0, 0, 1, divided by 3, 4 over 3, 2 over 3, 2 over 3. So finally, the solution what we want is this one. It's our what we want as hat. But the hat is exactly our C1, C2, C1, C2. So what's the function? You should remember that our original form is y equals C1 plus C2x. This one. So C1 is 4. So the best linear least square fit is y equals C1 is exactly 4 over 3 by its constant plus C2 is 2 over 3 times x. This one. This one. But now for this one we just consider linear function. I mean we consider the form y equals C1 plus C2x. So it's something like just its degree is 1. But if we want to get the best, probably we could consider a higher degree polynomial, not just linear function to solve it. And for this one, you could see the text in our textbook, page 232. You could see that. For example, projective or another function. Yeah, I mean it's the last remark. I mean we could use a higher degree polynomial. Here it means they're not linear functional, not just linear function. Yeah, and you could see textbook page 32. I mean page 232. Yeah, and here a higher degree, for example quadratic. It means that the power p, the power equals 2. If it's linear function, the power is 1, yeah, or 0, and quadratic, then its power is 2. Okay, and I give you the homework problem in this section. Homework problem in section 5.3. You could practice by yourself. 1b, 2a, 3a, 5a. Homework problem. Yeah. Okay. And if you have any questions, you could discuss.